Okay, so question 1. Initially considering alternating EMF and explaining why it's induced, an alternating EMF is induced in the secondary coil. Part B, in terms of electrical power, explain why the current through the primary coil of a transformer increases when a device is connected to the secondary coil. And so we've got to do this in terms of electrical power. So, if I look across at this, oops, that didn't quite work. Let's bring the camera up. There we go. We're going to assume we're working with an ideal transformer. To answer this question, and that transformer we take to be 100% efficient. Okay. Now, what does that mean? If my efficiency is 1, then my useful power out divided by my total power in must be 1. So that means the current in the secondary times the voltage in the secondary must be the current in the divided by the current in the primary divided by the voltage in the primary must be 1 divided by the other must be 1. And all I'm using there is power equals current times voltage. So if I play around with this a little bit, taking IP and VP over to the other side, I can then see that IP VP, so the power in, must be equal to the power out. So let's think about what this actually means. So when there's no device connected, there is no load. Alright, there's nothing to be taking energy out of the secondary. There's no load upon it. So, if there is no load, there's no power out. And now, that means your current through the secondary must be equal to 0. And the reason it means that is because the voltage across the secondary is probably going to be non-equal. They're not equal to 0 because an EMF will be induced, or is still induced. But there is no complete circuit allowing a current. So you've got a scenario here where you're inducing a voltage across the secondary, but there's no power out because there's no complete circuit because there's no current. So there's no current, so there's no power out. So therefore, if there's no load, current through the secondary is equal to 0. Now, the only way, if the current through the secondary is 0, the power out is 0. The voltage being applied in is non-zero. Therefore, there must be 0 current in the primary. So, the current through the primary is also 0. I'll put amps on there. I should probably be using amps throughout anyway, but there we go, so there's a current. Alright, so we've seen that if there's no load on the output, there's no connection. If I give you an idea what I mean, or just to make sure we're really clear on what I mean by that, what we're doing in this scenario is we've got our transformer, and we've got an AC applied across it, but all we've got across here is a voltmeter, and an ideal voltmeter is so this is a scenario of low load. An ideal voltmeter's got infinite resistance. So that's no load. With a load, the scenario we've got is we've still got the AC power supply going into it. There's my transformer. But we've now got, for example, a motor as well as a voltmeter across it. So this means we can actually get a current to flow in that leg of, or in that part of the circuit. So there must be a current flowing through here. So let's think about this. We've now added load. So if we add a load, there's now power out. Of the secondary coil. Or power out of the transformer. So therefore we know IS must be greater than 0. Because there's actually a current out now. So the current through the secondary must be greater than 0. Now, if power out has to equal to power in, if IS is non-zero, VS is non-zero, IP must now be non-zero. Otherwise you couldn't get any power going in. So that tells us if IS is greater than 0, IP must be greater than 0. So by adding, in summary, by adding a load to the secondary, the current in the primary has increased from the 0 current there was when there was no load across the secondary. Hopefully that makes sense. Thank you very much.